Okay. Good afternoon. Hello, everyone. So, today we are going to continue our lecture. But before that, have you submit all the additional works for polymer? Yeah. Okay. Uh, I think if you want to check your score this Thursday, okay? I forgot to bring the paper. But average is, I think, around maybe 40, around 40 average. So I hope the works that you've done that can add in the midterm score. Okay. So we learned at the beginning mostly before the midterm exam. We learned mostly about the polymer synthesis, right? The step growth, chain growth, and some detail, okay? How the kinetics, the degree of polymerization, and so on and so forth. Now, after the midterm, we are going to focus. Okay? We are going to focus the polymer on mostly either the architecture, the process, and also I think the characterization. That will be the main aspect. But still, we are having one more lecture on synthesis. So this is the last part about synthesis. Okay, this section. Okay. So this will be the polymer synthesis 4. So we are going to look at the sections. We will see that we are going to elaborate ionic polymerization, living radical polymerization, and the Ziegler-Napier catalyst. Okay. So I think there are actually more, but I think we are going to focus only these three. Okay. So ionic, living, radical, and Ziegler-Napier catalyst. Okay. So I hope today and maybe Thursday we are going to solve all of this. But I think today, because actually not really that much, but there are some details that we need to know, and at least you know the principle, okay? Although maybe not all the reactions and the formula, but at least the principle behind of all this synthesis. Okay, so let's start with the ionic polymerizations. So the ionic polymerizations, as the name suggests, so we are going to see the polymerization based on ions. Okay, so if you remember, in the chain growth we focus on the radicals, and now we focus on the ions. So the active center in chain growth or in free radical, we remember that mostly they are coming from the final monomer at the double bond, right? In the chain growth. Now we shifted and considered that the active one is coming from the ions, the carbocations or carbon ions. So it's the C with positive charge and the negative charge. Right? So that we consider as our active species, and so these two will be our active species that will polymerize. Okay? That will start the polymerization. And the main difference, if we are considering what's the difference between the ionic polymerizations with the regular radical polymerization or the free radical polymerization, is there will be no annihilation of two active centers. Okay, remember, in chain growth polymerizations, if you want to terminate the polymerization, we are going to terminate and we are going to annihilate, to remove the active center by taking two active centers together. So they will be eliminated at the same time. So the radical will be removed, right? But now there will be no such things in ionic polymerization. Because if we consider the ions they are considered as having high energy, right? Having high energy. They need to have stabilizers. So we need to have some substituents that is stabilized, okay? that can stabilize this energetic species. Okay. So if we have this cationic, so if we have this positive charge, okay, this carbon positive, so if this is our active centers, then how the polymerization will occur is if, you see here, I'm taking the bold for some words, donate electrons. So if we have some group that can donate electrons to this positive charge, okay, because it's positive charge, that is easy to donate electrons, okay, for the groups, for the substituent groups. Okay. Or we can say it's delocalized the positive charge. So then we can see the polymerization. Okay? So remember, positive charge, then the groups need to donate electrons. So donate electrons here. Okay, so this will polymerize. Okay. And just a reminder, I hope everyone finished their additional works for the polymer. Okay. And your score, I think Thursday I can deliver. Okay. Actually, it has all done, okay. But I want to make sure your works, and then we'll just deliver this Thursday. Okay, this is the carbocation. And for the anionic, for the negative charge, you see, because it's now negative, then what will happen is the group needs to have something that can withdraw the electrons. So if the positive can donor, the negative can withdraw. So they need electrons, because they need electrons. Or we can say they can delocalize the negative charge. So then they can take the polymerization on the active centers. Okay? So that's the basics. That's the basics. So we are going to take this behavior on these ions. Either carbocation or carbanion, cationic or anionic, we can see how they behave, and we can take that as our principle for polymerization. Okay? Okay, some monomer, okay, that can we can consider. Let me just take it clearly. So we can have some monomers that can be categorized as a radical, cationic, or anionic. Okay? So if you see, we have ethylene, it's a regular final monomer. You can consider this ethylene as a radical in free radical relationship, or we can also consider this cationic if we want to make sure that we use its active center, the ion active center. Okay. And then we have the propylene on the alkyl olefins, and it's considered it's not really that good. Okay. This actually can be done, but it's not as easy as this one. Okay. so considered not really good. And dialkyl olefins is good for the cationic. Okay. So this is because we have the R here, okay. And this is only one. Dienes considered for all radical and the ionic, both positive and negative charge, they can be used, and so on and so forth. We can see from all these monomers, okay. So sometimes one monomer can be used in regular radical polymerization, or we can choose between either cationic or anionic. Now, before we've gone through the process, let's try to look at the how we prepare. Okay. So first is the active centers. It needs to be prepared by some reactions. Okay. So usually we take this boron fluoride. So we need to make sure that it has the protonic acid, okay, as this H plus. Okay. So we are going to use this as our initiators, or to initiate the polymerizations. Okay, I think. Okay, this is the first step. Okay, so this is to prepare the initiator. So we need to create the electrophiles. So this is initiator. Okay, and the second step is propagating. Okay, so we are going to see that the double bond here will break. This will break. Okay, break because of this positive charge here. Okay, so this is what we call before the donors. So the electron within this double bond will be considered as a donor. Okay? So we take the electrons and then move to these positive ions. And then we have, in the result here, we're going to have this. Okay? And then we still have another active center. And this will also polymerize. Okay? So if we still have more concentrations, so this will also attract the electron, and then it will adding the monomers. Okay. So we can consider this, okay, to react with another monomers, okay, and then it will grow and grow, and we can consider perhaps with some repetitions for the unit, and still maybe it still have more active center, and then it can do more and more. But then we still have, at the end, we still have these ions. Okay, still have these ions. So we need to terminate this, right? So if you want to read in more official definitions, so the second step, it involves electrons from the pi bond, which means this one, pi bond here, it's joining to H plus, and then creating this bond here, and then it's leaving an empty orbital. Which one? This one. So create this and leaving an empty orbital. And of course, because of this behavior, the monomers will be limited, as we see from the table, will be limited for cationic. Okay. And this is if you want to make it more general. Okay, so RA is more general. So the idea is the R is electrophile, and the A is the counter ion. Okay. As long as the monomer and the initiator, they can fit within this principle, we can use the cationic polymerizations. Okay, and then the propagations, as we see, it goes by, we call the name as a head to tail additions. Okay, this is what we discussed before. So we see that it is going to be donor the electrons, donor electrons, okay, from the double bond to the active centers, which it can polymerize. So how we can terminate? So basically, it can terminate by rearrangement. Okay. So let me go through here. This is the terminations. So terminations. So for two propagating chains, if we consider a reaction, ionic polymerization is not possible. So not possible for ionic, okay, because of the repulsion charge. Okay. Okay. So remember, in radical polymerizations in the chain growth, because it's just radical species, they meet with another radical, they can annihilate, and then they can react with themselves. But now we have the positive charge. If positive charge meets with positive charge, it will repulse. Okay? It will not be any annihilation. So what we need is just a molecular rearrangement. Okay? So if we see here, okay, we have this CH2 right here. So one of them, they will rearrange, and the bond will broken from this CH bond. So we are going to rearrange and make this double bond, and the other hydrogen will going to be the counter ion. Okay, and we will At least it will stable. It will be a stable. Okay. But this part we can reinitiate. If you want to polymerize this part to break this double bond, we can make again. Okay. So this is, we can say it can be terminated and it can be initiated again. Okay. So we say this one here is terminated, but can be reinitiated. So in terms of adjustment, although not many monomers can be treated within this method, because how we can adjust the polymerizations, both cationic and anionic, it's more considered easier. Okay, considered easier to adjust. Okay? Because technically it's not really terminated, so we can reinitiate again and again. Okay? So it's easy to polymerize that. The only I think drawback is the not many monomers that can be prepared. Okay. So as I mentioned before, so this lecture, the synthesis part, this will be the last part of the synthesis of our course. Okay? So after this, we are going to see more visuals, characterizations, structure, and process. How to process the polymers, like in industry, how to prepare, how to take moldings, how to make polymer moldings and others. Okay. Okay, so actually, the half part of our course is synthesis, like the step growth, chain growth, okay, like your meter. They consider more technical, and now it's more I consider more like knowledge based, so not really having much formula or computations or calculations. Okay, and also aside from termination, we can also consider a chain transfer. Okay, so chain transfer also possible. So like we see from here. So if you want to terminate, like if you want to rearrange this this hydrogen, so you want to abstract, and then it's going to meet with this double bond again. So we get another active center. So it's basically, we say we transfer the active center to another monomer. Okay. So this is also can happen. So we can have a chain transfer to monomer. Okay, I forgot to take some example for monomers. Let me make some table for you. So one of the example, the commercial one, monomers, this is initiator is BF3 H2O component. and application. This is for elastomer and adhesive. This is vinyl ester. Oh, vinyl ester, sorry. Same system. This is also for adhesive and also for plasticizer. Trioxane. This is BF3. This is for construction, for antimicrobial coatings. Some also for stealth nano coatings. This is ethylene imine. This is protonic acid. Also for the THF. THF is tetrahydrofuran. It's usually a solvent. Non-polar solvent. This is paper additive. This is plasticizer, usually for polyurethane and polyethylene elastomer. Okay. I think we can take this. Okay, I think we can move to the next one. So we are going to have the anionic polymerization. So this is considered early studies. The idea for this one is need to have a strong base for initiators. Okay, because we want to make sure that the active center is the negative ion. So first is in initiations, we usually use the potassium amide, so KNH2. So we can dissociate this with, so we have positive and negative, right? So this is 1, and 2 is more advanced. This is, we call the organometallic compounds like butyllithium. So we have 2 butyl and lithium, which this is going to have. Butyl is more electronegative, and lithium is more positive in this electronegativity. And then we can use each ion like that. And butyl is exceptionally volatile and flammable, so it's easily burned. Later we are going to see the second one, because the second one is more advanced and it's more the usage is really broad, while the first one, the potassium amides, I think it's in a sense of principle of ionic, we can consider that as our first steps, but eventually the second one is more advanced, and we are going to see a lot of this, the second example. This is, we call the organometallic compounds. Okay, let's see the potassium amides first. So the initiations, we separate the ions, positive and negative, and then we are going to using the amides with negative charge. We take that as our initiators, and this will be the monomer. And if you see the double bond, as usual, it's going to be polymerized. Okay, it's going to polymerize, and then the negative charge will shift it to this, okay, this carbon here, and then they are going to reiterate for every end. Okay, so it will propagate, and propagate, and the side directions will be resulting in this double bond. If you remember, I is for initiators, propagations, and for transfer. So it will propagate and propagate until here. And then at the end, we can transfer this active centers, we can transfer to this solvent. NH3. So we are going to transfer this negative to this solvent NH3. So then we can stabilize the monomers, which becomes a polymer. Okay. So we consider the terminations, not really terminations. It's just the chain transfer. Okay. So we chain transfer the active center to another ions. Okay. Okay, so that's the ions from the NH3, and it will stabilize, and the side product is, the byproduct is the ions. Okay. But we successfully get the result. And we get the result. So initiations dissociate the kalium, the potassium, and the amides, and then addition, okay, addition the amide to styrene. Okay, so this is styrene. So styrene, okay, just a side note, styrene, it works both ways. So it works in cationic and also works in anionic. Okay, because it has the benzene rings, so we can have a shifted electrons and make it more positive charge or negative charge. So if we see if this is a styrene, if we take initiator that is preparing to be a positive, this electron will take this because of the initiator. So we are going to have a positive charge, and then it will be shifted around and shifted around. So we are going to have different active centers. It depends on the case. So we have a cationics, or we can also have styrene that prepare from the anionic. So for example, the styrene that we can have is if we have to take double bond here and then take a styrene here. If you have the double bond, then we can take this, and this will be reacted to that sides, and we get and in the same way this will be going to be negative, and then it will be we have a shifted electrons. So we can take this as a negative in these three sides. Okay, so we can have some shifted active centers. So it works in cationic, it works in an anionic, it works. It depends on the initiator. Okay, so for styrene, you can have both way. So this is the original anionic polymerization. And basically, what we've seen here, since this is not really terminated, okay, this is just transferring the active centers, right? So we can consider that one of the important features for the anionic polymerizations is they are not be able to have the inherent termination process. Okay. So if we are like from the previous one, if we didn't put the reaction in the solvent, then the chain transfer will not occur and the polymerization will still happening. So it is going to be a reaction without any termination. This is really important to take notes. So absence of inherent termination process. And somewhat we can say this is what we call the living. So it's actually saying that the polymers, it goes on without stop. So without any stopping point. So you can consider it's like a living polymerization. It says that polymers didn't die. Okay, before we get the idea that we are going to take this into another set of reactions, let's see the butyl lithium. Okay. Okay, let's see the butyl lithium. So butyl lithium. Butyl lithium. So remember, you can take this and make this as our initiator. So we are going to use this and then adding to the monomer. So this X is any electron withdrawings. And then our expectations with this initiator is to react with this monomer, and the butyl will get into this monomer and taking this form, while it has the negative charge on this carbon ions. So this is the carbon ion. And then the lithium becomes the ion. And then within this carbon ions, we can polymerize further. Okay. So polymerize further. So take another monomer. Okay. And again, we can have a polymer chain through this active center. So perhaps this is going to be this way. So we have two now. So this is the active center, and this is the lithium. And perhaps more and more monomers react, and then we can take this and then perhaps we can have some n repeat units, and this still have the active center, and then we have the lithium. So if you think how to terminate this, it will be not possible. So any choices of maybe some solutions, polymer, or anything, it is really difficult to find something to stop this. Maybe we can, but it will not be permanent. It's not permanent. Okay, so let's continue. So we said here, it's impossible to terminate by itself. So the anionic polymerizations. So if you remember, in cationic, the termination is not possible because of the charge repulsion, right? And then in anionic, okay, if you want to have a more clear official definitions, in ionic polymerizations, the terminations by ion pair rearrangement, okay, is also not possible. It doesn't occur. Okay, see, ion pair rearrangement it doesn't occur. Okay, so if we see the cationic, we can have the molecular arrangement, but in ionic, we need to have to eliminate the hydride ion, okay, because so the idea is actually if you want to terminate, the negative charge need to become double bond, which is not possible. Okay. So because it requires to eliminate a hydride ion, the hydroxide, the hydrate ion, so this is not possible. Okay. And if you read here, okay, if you want to make sure that we understand what it is, so the alkali metal counter ions, okay, the alkali used to have no tendency to combine. So it has no tendency to combine with the carbon active centers from unreactive covalent bonds, and because no chain transfer, so because no chain transfer due to absence of chain transfer, different from the previous cationic, which we can have some chain transfer, and the potassium amide, we can have chain transfer to NH3, the solvent. But in the organometallic, in the alkali metal counter ions, we cannot have any chain transfer. So the monomer will start to polymerize and start to propagating, and it will go further without stop. So we consider this a living. Okay. So it retains their active carbanionic end group. So it's going to. So we will go through propagating all the time. Okay. So we consider it's a living. So it's retain the active center, the negative charge active center groups, and it's on and on. Okay. So if you want to summarize this, first, no recombination. no hydride ions, right? And no inherent terminations. Okay. Okay, so this is just a quick notes. So the organolithium, the butyl lithium, for example, it's most widely used organometallic initiators for this anionic polymerizations. So if we want to make some statement, so let me write again. So no recombination, no H minus, and no inherent termination. But we can force deactivations. For example, if we take this and plus with this, let's say it has unpaired electron here. So since the carbon is more positive, so this charge is attracted to that carbon. Okay. And this will force these reactions. Or let's say this is just R. Okay, this is R, R, and then this is another. Carbon. And then we need to remove one of the double bond. So let's say remove this. So we can have one side is having more electrons. And this is the active centers. And let's say we are going to take it into HCl. So it will react to the H plus. So the Cl will be going over here. So we can say this will be N group functionalizations. Okay, and this is some more general definition for propagations. So propagations is predominantly head-to-tail additions of monomer because of the steric and electronic effects on the stability of the carbon ion. Okay, the Mt plus is the metal counter ion. Okay. So this is actually what we have seen in the in butyl lithium also. Okay. So we introduce the monomer, we break the bond, the double bond, okay, and then we polymerize through the negative charge. So this is how we can actually, it's not terminated but deactivated, because we can activate it again, okay, after it finished. So we can take it into some proton donors, let's say for example the alcohols, okay, or maybe the acids. Okay. So the idea is to abstract the H from the alcohols. Okay. So the H will move to the active centers, while the metal, the alkali metals, for example, will be going to the as a byproduct here. So we can say this part has been deactivated. Okay. So that part is become deactivated. So we can end or but remember that this is not permanent. Okay, so this is not permanent. Not permanent. Which means we can activate it in the future. And another routes that we can have. Okay, this is, as I mentioned, we can dilute with acid, okay, with HCl, for example, and it ends with the carboxylic acid end group. Okay, and the idea is still the same. So the active center goes here, break the bond, okay, and the metal will go around here, okay, and then finally it will make this carboxylic acid. So we can dilute with the acid. So the idea is the acid is because it can also donor the H plus. Another route is both acid and actually this is just the difference on this part here. Okay. So we can actually induce the active center and make sure that it's propagating through here. Okay. And then take the acid, so that the can donors the proton. So we can have an alcohol, and this is just an idea for how we can have the reactions. Okay. And it's also another. Oh, I think this is the same. Oh, the different monomers. Okay, different monomers, but still with the same principle. And it will deactivate the polymerizations. Okay. Now let's go through the consequences. Okay. What will be the consequences for the anionic polymerizations? first, it's very good to control the molecular weight. Why? Why? Why it's good to control? Any idea? Okay, remember, in a step growth, it's difficult to control because you have to build the molecular weight like slowly, and it doesn't have like at the early stage. We are not seeing any molecular weight at the beginning. Right? Yeah, we need to take some time, slowly, and then it will be having exponential at the end, right? And if we take the chain growth, we can have it as early as possible for the molecular weight. And the difficulty between the step growth and chain growth, in step growth, you can have really pure, really high conversions for the molecular weight. So you can have like 99%. But for the chain growth, sometimes 99% is really difficult to achieve because if you are not really adjust your kinetics at the beginning, then if it's already built the molecular weight, then you cannot do anything about it. But here, it says it's very good to control molecular weight. How is it possible? How is it possible? Any idea? Why is it easy to control molecular weight? Any comments, suggestions? Okay, consider the ionic polymerizations, as I mentioned at the beginning, does not have any termination screw. Right? I said that the terminations can be either if we have a chain transfer, or if we have like the activations, like if we react with another and we force to stop for a while. Okay, stop for a while, then you can have polymerization again later. So it's not really kind of a terminating process, right? And because of that, so whatever monomers we have, as long as it can polymerize within ionic polymerizations, we can just throw anything, and then the monomers just polymerize itself, right? So because it will polymerize all monomers at the same time, so we don't really need to like control everything. What we need to control is the beginning of the process. If we have good choice of monomers, we first make sure that it can have the ionic property, okay, and everything and so on. Then it will polymerize by itself. So not to worry about everything. So you can say all monomer added at the same time. It's I think easy to control the molecular weight, right? Because we just put everything together, right? And then the polymerization will start at the same time, which means we are going to have a narrow distribution. So low PDI. What is PDI? What is PDI? P maybe poly, right? D is what? PDI, what is PDI? And why is having low PDI? What? Yeah, poly dispersity index. So what does it mean if you have the low PDI? Well, it means that it's narrow distribution. Okay, it's a narrow distribution, which means that because you remember, if you think about polymer, we think on the like large molecules, right? Large molecules, like it has like like if you imagine like chains, like there's short chain, longer chain, and everything into one, then how we measure will be different if we take different angles, right? If we take from this perspective, maybe this has this is its weight, this is its weight, and we have like average molecular weight, right? So we can have like distribution molecular weight, right? And if we make it into like narrow distributions, which means that the chance we get really good polymers is high, right? Because it has a narrow distribution. Okay, so for example, if I have a broad distribution, okay, I buy polymer, maybe the result is it's not really good, maybe it's small. I think maybe this polymer, oh no, it's also small here, but it is having low PDI. So consider we have this, and consider we have that. Okay. This is polymer A. This is polymer B. If we buy polymer A, perhaps if we doing it in an experiment, we make some product, maybe we get this right, small molecular weight. We want this. When we make B, the probability we get this is quite high, right? Because you only have this. Okay? The percentage on having good molecular weight is high. Okay. Okay, and then it has very long polymer chains because of the ionic. Okay. And then it can synthesis of block copolymers. So it's possible. It's possible to synthesize. Which means that we can think the block copolymers as if we want to make like having different segments in one chain, it's possible. And if we think in molecular weight, if we think in the degree of polymerizations, the step growth is like this. Right, this is step growth. To give you an idea, and this is the radical or the chain growth. Okay. And how about the anionic? Okay, the living polymerizations. Anionic is it here. It's going to be linear. So living polymerizations. And the consequence is also we get some disadvantage, which is first is the conditions. And to make sure the conditions is possible for the anionic polymerizations, and then not many monomers that we can obtain. Okay. So it's just limited monomers. So this is percentage, this is the P, and this is the XN, or maybe this is for molecular weight. Or maybe P, better using P, the percentage. Okay, now from this idea of this living polymerization from the anionic polymerization, now if we can consider, if we can make something in polymerizations, we can make the polymerizations never stop. like it's always polymerized, but then it's not using ions. So perhaps if we take radical, the active species for radicals, and make radicals goes and on and on. Okay. So can we make polymerizations living with radicals? Okay, so that's the questions, the premise. So how to make radical polymerizations, or the chain growth, is living, okay, which means that it's not going to stop. It's not going to stop. So the idea is we are going to adjust the radical. Okay? How to adjust the radical is basically how we adjust the ions. Okay? If we can deactivate the ions, the negative charge, then we can also make something for the radical. So we can maybe deactivate the radical. So principle is first deactivated or reversibly deactivated. So it will be temporarily. So then we can control radical polymerizations. So if we can activate and then activate, then it means that we can control. Okay. So that's the idea, to make the radical polymerizations like living. So we call this method is living radical polymerizations. Okay, and this is quite advanced method. Up until now, it's still considered as a quite advanced method, especially related to some metallic compounds that need to be, because it has some advancement in chain transfer and so on. It's still considered as one method to accomplish some complex polymers. Okay, so this is what we have as a concept, like I mentioned. It needs to be reversibly deactivated, or we can say it's trapped. Okay, so we need to make some trap. Okay, what does it mean? What does this trap mean? Okay. Remember, the radical species is the one that is really active, right? You consider in like dot in the chemistry, right? In the reaction. So what this means is, if we can make some shield, okay? For example, if we can take this is a radical, and we can make something that blocks this radical from the environment, that's also possible. So we need to make maybe some like a shielding the radical, okay. And then to activate, then we need to make sure that we can react something with this shield, okay, to make the shield open. Okay. So we can say this is what we call reversible deactivation radical polymerization. So there will be several strategies. I think just two strategies at the most. Okay. First is using metal complex, as we see later. This is strategy 1. So strategy 1, I forgot to mention strategy 1. We call the reversible capping. Capping is like a shield. You can say shielding also is the same. Cap is like a hat, okay? So it's to close something. So close the radical. Okay? This is to shield the radical. So the principle is to take the concentrations for the radical itself to be reduced. Okay? So highly reduced. Example is, we say this is the atom transfer radical polymerizations. Okay, so the polymer is really like a vast amount of either the reference, the principles, because they are really broad subject on this polymer systems, right? Like from the beginning, we see some fundamental concept, how we see synthesis. There are have several different syntheses, and we are just touching the, I think, not really all synthesis, because there are more synthesis, like there are what we call one-click chemistry. That is also another concept in chemistry that is also related to polymer. We also have other method as well that is maybe not included in our lecture. But these lectures serve as introductions. So it doesn't mean that you need to know everything about polymer. So what you need to know is basically, in some lectures, I wrote something like an emphasis, something that's the one that you need to take on. Okay? Not all the reactions need to be remember the formula and everything, but some emphasis, like the principle like this one, that you need to know, because if you are going to take master or maybe take something to do with research, for example, while doing research, you still need to to remember what does it mean and then how does it work, right? So it doesn't work always like you need to remember everything, because at the end of the day you are going to read more books, and read more books, and somehow if you are still, maybe today you are I don't think this is really fit with my knowledge, but someday later you will know, when you learn, and maybe you will experience the real practice in life, and perhaps you are able to know, oh, I know this. So I'm not expecting you know everything about this. Okay. But anyway, let's get on to the example here. So this is the strategy. Okay. What we call the reversible end capping of a chain radical. So this is strategy 1. Okay. We introduce end capping of chain radical. Okay, so let's say we are looking from here, and then This is the result. Okay? And it is reversible. So we can see from the left going to the right, and from the right going to the left. Okay? So we can activate, deactivate, okay? So idea is this radical will be annihilated with some other species. So it's like you have a pen, you have a cap for a pen. So it's like, okay, you put the cap on the pen, so the pen is not going to be exposed. So this radical is not exposed. So it's closed now. Okay. So this is what we call the dormant species. Okay. So the dormant species. This is the dormant species. And usually we are going to utilize the metal complex. And then you see that the equilibrium is not the same, right and left, right? This is short, this is long. So what does it mean? So it's shorter, but so to open the cap is shorter than to close the cap. So we need to make sure that the reaction is pushing to the dormant. Okay? Because we want to make sure that we can control the reaction. Okay? So if we are having maybe the reaction is more on right side, then we are not able to control it. Okay? Because it's going to be a radical. We can control the radical. But if we can make sure it's going to close, the radical is going to be entrapped inside this cap, then we can control, basically. That's the idea. Okay? So we need to make sure that the this equilibrium, we need to adjust equilibrium to push to dormant so that we can control. And how to control this is basically what we see from this side here. So the concentrations, so if you remember the principle, of the radical is strongly reduced. So we are going to use this to denote the polymerization. So if you remember, the rate of polymerization is proportional to this side, right? So if we can take this strongly reduced, then the rate of polymerization is also reduced. Okay? So that's the idea. So that's how we can take the polymerization and make it into dormant species so that we can control it. So there are some steps. If you want to look on specific steps, so we prepare the organic halide initiator, and then the chlorine carbon will reversibly breaks, okay? And then because of the electron transfer, and then radical is formed. That's the active state, the right side, and then we can take back and forward through the equilibrium and make sure we push to the dormant. Okay, so we can deactivate by back reactions. Okay, so we push to the dormant state, and this is some choices for initiator. So the chloride or Br, okay, or bromine, chlorine or bromine. You can choose halides from those two. We can take this or this. I think it depends on conditions. But they are a typical initiator. forgot. So by the end of these steps, okay, the termination strongly suppress. This is by okay, as I mentioned here, we are using the metal complex for the cap for the shield. Okay, this is some of the example. Okay, if we look on how the idea, okay, so this is a transition metal catalyzed radical polymerization. So let me put principle of transition metal catalyzed radical polymerization. Or we can just say the ATRP. So we see that in this chain radical, okay, the chain radical will be released and it will be captured. Okay. So here we see radical from this Rx is going to be R like that. And basically what it says is this radical will be trapped. Okay. Now if we see, this is how the radical is trapped, okay, inside. So we are going to use this metal complexes. If we want to make it activate, then we can adjust the metal complex, and then we can take this into a radical. So we can make this side active, okay? And then by itself, it can add more. It can add more monomers. This monomer, so you can add more and more, or it can be terminate by itself because it has a radical. Okay? So it can also terminate. So we can need to adjust equilibrium, which one we are going to take. So we can make sure that maybe we want to make the polymers that has some certain molecular weight, okay, or we can terminate just as it is, and then as a byproduct we have the metal complex. You'll see that we need to push the side here to this side. So that we can control further. So I think I will end up until here. We are going to maybe take some notes from this ATRP more. And yeah, I think we're going to have this second strategy in Thursday. Okay. And maybe continuation. If Thursday is not enough, then in next Monday class. Okay. So I think that's it for today. So this synthesis is the last part of synthesis for whole lecture. Okay? So this is the last synthesis, okay, for you. Okay? This polymer synthesis 4 will be the last. So after that, we are going to see in other different aspects. Okay? In the structure, the characterizations, process. Okay? So yeah, I think that's it for today.